Let me start with a question that seems simple. How old is the universe? You probably know the answer. Scientists say the universe is about 13.8 billion years old. That's what you read in textbooks. That's what astronomers tell us. That's the official number for measurements of the cosmic microwave background radiation. Except here's the problem. That number is wrong. Not slightly wrong, fundamentally wrong. And I don't mean it's off by a few million years. I mean the entire question, how old is the universe, doesn't even make sense the way most people think it does. I'm Leonard Susskind, and I've spent decades working on cosmology, black holes, and the nature of time itself. And I can tell you that when we say the universe is 13.8 billion years old, we're making assumptions that break down when you really understand general relativity and quantum mechanics. The age of the universe depends on who's measuring it, where they are, how fast they're moving, and in some reference frames, the universe might not have an age at all. Time doesn't work the way you think it does. And once you understand why the universe's age is wrong, you'll never think about cosmology the same way again. So, let's start with what you've been told. The Big Bang happened 13.8 billion years ago. The universe has been expanding ever since. We can measure the rate of expansion. We can look at distant galaxies and see how fast they're moving away from us. We can measure the cosmic microwave background, the leftover radiation from the early universe. All of this data points to an age of about 13.8 billion years. Case closed. Right? Wrong. Because here's the first problem. 13.8 billion years according to whose clock time is not absolute. Einstein showed us this over a century ago. Time runs at different rates depending on your motion and your position in a gravitational field. A clock on Earth runs at a different rate than a clock on a GPS satellite. A clock near a black hole runs slower than a clock far away from it. Time is relative. So when we say the universe is 13.8 billion years old, we need to ask whose 13.8 billion years are we talking about? The answer is we're measuring time according to what physicists call a co-moving observer. This is an imaginary observer who's at rest with respect to the expansion of the universe. An observer who sees the cosmic microwave background as uniform in all directions. If you're moving through space relative to the cosmic microwave background, you're not a moving observer. Your clock runs at a different rate. You would measure a different age for the universe. Now, you might say, okay, fine, but that's just a technicality. We can define what we mean by the age of the universe and then measure it. And that's true. For a calm moving observer, the universe is 13.8 billion years old. But here's where it gets really strange. Not everyone can be a calm moving observer. And in fact, there are perfectly valid reference frames in which the universe has a completely different age or no well-defined age at all. Let me give you an example. Imagine you're traveling through space at very high speed, close to the speed of light. From your perspective, time dilation is extreme. Billions of years on a co-moving clock might correspond to much less time on your clock. If you were traveling fast enough, you could traverse the entire observable universe in what feels like a few years to you, even though billions of years pass for observers at rest. So from your perspective, has 13.8 billion years passed since the Big Bang? No, much less time has passed. So what's the age of the universe? It depends on who's asking. But it gets worse. Much worse. Let's talk about the Big Bang itself. We say the Big Bang happened 13.8 billion years ago. But what does that even mean? The Big Bang wasn't an event that happened at a particular place. It happened everywhere. Every point in space was part of the Big Bang. Space itself was compressed to an infinite decimal size. And here's the key point. Time itself was different at the Big Bang. In general relativity, time is part of spacing. It's woven together with space. And near the Big Bang, the geometry of space-time was so extreme that our normal notions of time break down. At the very instant of the Big Bang, at what we call time equals zero, the temperature was infinite. The density was infinite. The curvature of spacing was infinite. These infinities tell us that our theory is breaking down. We're reaching the limits of general relativity. What this means is that we can't actually go all the way back to time zero. Our physics only works from about 10 to the minus 43 seconds after the Big Bang. This is called the Planck Time. Before the Planck Time, we need a theory of quantum gravity, which we don't have. So when we say the Big Bang happened 13.8 billion years ago, we really mean that 13.88 billion years ago, the universe was in an extremely hot, dense state. But we can't actually say what happened at the very beginning. We can't say when time started or if time even had a beginning in any meaningful sense. Now, let me tell you about something even stranger: the expansion of the universe. You've been told that the universe is expanding. Galaxies are moving away from us. Space itself is stretching, and all of this is true. But here's what they don't tell you. The expansion affects how we measure time. In an expanding universe, the geometry of spacing is changing. And this means that the rate at which time passes is different in different epochs of cosmic history. Think about it this way. The cosmic microwave background radiation that we see today was emitted about 380,000 years after the Big Bang. But those are years measured in the reference frame of the early universe. The universe was much smaller then, much hotter. The geometry of spacing was different. When we say 380,000 years, we're using our current definition of what a year is. But the actual geometry of space-time then was so different that it's not clear this comparison even makes sense. Here's an analogy. Imagine you're trying to measure the age of a balloon that's being inflated. You mark 2 points on the balloon and measure the distance between them. As the balloon inflates, the distance increases. Now you try to measure how long ago the balloon was much smaller. You can work backwards using the rate of expansion. But here's the problem. The surface of the balloon is stretching. The geometry is changing. A cime on the early balloon is not the same as a centimeter on the inflated balloon. They're different geometries, different coordinate systems. The same thing happens with the universe. The universe 13.8 billion years ago was in a completely different geometric state than it is now. When we say it was 13.8 billion years ago, we're projecting our current notion of time backwards. But time itself was different. Then the geometry was different. The comparison might not even be meaningful. Now let me talk about something that really blows apart our notion of the universe's age, the cosmological horizon. This is the boundary of the observable universe. It's not a physical boundary. It's a limitation on what we can see based on the finite speed of light and the finite age of the universe. Light from beyond the cosmological horizon hasn't had time to reach us yet. So we can't see it. We can't observe it. It's beyond our observable universe. But here's the crucial point. Different observers have different cosmological horizons. An observer in a distant galaxy sees a different portion of the universe than we do. Their observable universe is centered on them, not on us. And in general relativity, there's no preferred observer, no special reference frame. Every observer is equally valid. So whose cosmological horizon defines the age of the universe? Whose observable universe are we talking about? You might say, well, we're talking about our observable universe, the universe as we can see it from Earth. And that's fine. We can define things that way. But then we have to be honest when we say the universe is 13.88 billion years old. We mean our observable universe appears to us to be 13.8 billion years old measured in our reference frame. That's a lot of qualifiers. That's a very different statement than saying the universe is 13.8 billion years old as some absolute fact. And it gets even more complicated when you think about regions of space that are moving away from us faster than the speed of light. Yes, this is possible. The expansion of space itself is not limited by the speed of light. Objects can recede from us faster than light, not because they're moving through space faster than light, but because space itself is expanding between us. For these distant regions, our notion of simultaneity breaks down completely. We can't even define what it means for something to be happening now. In those regions, time becomes ambiguous. Let me tell you about something I've worked on extensively: the cosmological constant and dark energy. We now know that the expansion of the universe is accelerating. Something we call dark energy is pushing space apart at an ever-increasing rate. This has profound implications for the age of the universe. If the expansion continues to accelerate, then in the far future, distant galaxies will recede from us faster and faster. Eventually, they'll cross our cosmological horizon. They'll move so far away that their light can never reach us. From our perspective, they'll effectively disappear from the universe. Now, here's the question. If a galaxy disappears from our observable universe, does it still exist? From our perspective, no. We can never see it. We can never interact with it. We can never receive information from it. It has effectively ceased to exist for us. But from the galaxy's perspective, it still exists. It's still there. Time is still passing. So which perspective is correct? Is the galaxy part of the universe or not? This is where the question of the universe's age becomes truly problematic. The universe's age depends not just on whose clock you're using, but on what you mean by the universe. Do you mean the entire universe, including parts we can never observe? Or do you mean the observable universe? And if you mean the observable universe, whose observable universe? These are not trivial questions. They go to the heart of what we mean by the age of the universe. Now, let me talk about something even more fundamental: the arrow of time. We experience time as flowing in one direction from past to future. Entropy increases. We remember the past, but not the future. Causes precede effects. This seems obvious, but in the fundamental laws of physics, time is symmetric. The equations work the same forwards and backwards. So why do we experience time as flowing in one direction? The answer has to do with the Big Bang. The early universe was in an extremely low entropy state. Everything was compressed, uniform, simple, and ever since then, entropy has been increasing. The universe has been getting more disordered, more complex, more spread out. And this increase in entropy gives us the arrow of time. It tells us which direction is the future. But here's the disturbing part. The Big Bang being a low entropy state is highly unlikely. In fact, it's so unlikely that it requires explanation. Why did the universe start in such an improbable state? We don't know. This is called the past hypothesis. It's an assumption we make about the initial conditions of the universe. But it's not explained by our current theories. We just assume it's true because otherwise the arrow of time doesn't make sense. And if we can't explain why the universe started in a low entropy state, then we can't really explain why time flows the way it does. And if we can't explain the arrow of time, then our notion of the age of the universe becomes even more problematic. What does it mean to say the universe is 13.8 billion years old? If we don't really understand why time flows forward, let me tell you about the horizon problem. In the cosmic microwave background radiation, we see that different regions of the sky have almost exactly the same temperature. They're uniform to about 1 part in a 100,000. But here's the problem. These regions are so far apart that light hasn't had time to travel between them since the Big Bang. They're beyond each other's cosmological horizons. So, how did they end up at the same temperature? How did they coordinate to be so uniform if they've never been in contact? The standard answer is inflation. The idea that in the first fraction of a second after the Big Bang, the universe expanded exponentially fast, much faster than the speed of light. During inflation, regions that are now separated were once in contact. They were once close enough to reach the same temperature. Then inflation stretched them apart to vast distances. This solves the horizon problem, but inflation has a strange implication for the age of the universe. During the inflationary period, time was passing in the usual way, but space was expanding exponentially. In a tiny fraction of a second, the universe grew by a factor of maybe 10 to the power of 30 or more. So in a sense, the universe aged very little during inflation, but grew incredibly old in terms of size. What does this do to our notion of the universe's age? Is age measured by time elapsed or by the amount of expansion? These give different answers during inflation. And here's something even stranger. In eternal inflation models, which many cosmologists take seriously, inflation never completely ends. It ends in some regions, creating bubble universes like ours, but in other regions it continues forever. New bubble universes are constantly being created. The multiverse is eternally inflating. So in this picture, our universe, our bubble has an age. It's been 13.8 billion years since inflation ended in our region. But the multiverse as a whole has no age. It's eternal. It's always been inflating and always will be. So what's the age of the universe? It depends on whether you're talking about our bubble or the whole multiverse. Now let me tell you about something that really challenges our notion of time. Black holes near a black hole time behaves very strangely. As you approach the event horizon, time slows down from the perspective of a distant observer. At the event horizon itself, time appears to stop. If you watch someone fall into a black hole, you never see them cross the horizon. They appear to freeze in time, getting redder and dimmer, but never quite disappearing. But from the perspective of the person falling in, nothing special happens at the horizon. They cross it in finite time on their own clock, and then they continue falling toward the singularity at the center. So whose perspective is right? Does the person cross the horizon or not? How much time has passed? It depends on the observer. There's no absolute answer. Now, think about this in the context of the Big Bang. Some cosmologists believe that the Big Bang singularity is similar to the singularity inside a black hole. If that's true, then the question of what happened at time zero might be as ill-defined as the question of what happens at the center of a black hole. Time might not extend all the way back to the singularity. There might not be a moment when time began. The age of the universe might not have a well-defined meaning. Here's something I've thought about a lot in my work: the holographic principle. This is the idea that all the information in a volume of space can be encoded on the boundary of that region. The three-dimensional volume is in some sense equivalent to information stored on a two-dimensional surface. This principle comes from studying black holes, but it seems to apply to the entire universe. If the holographic principle is correct, then the universe might be fundamentally two-dimensional. The three-dimensional space we experience might be emergent. It might arise from more fundamental two-dimensional physics at the boundary of the universe. And if space is emergent, then time might be emergent too. Time might not be a fundamental feature of reality. It might be something that emerges from deeper physics. And if time is emergent, then asking for the age of the universe is like asking for the age of a rainbow. Rainbows aren't fundamental objects. They're optical phenomena that emerge from sunlight and water droplets. They don't have an age in any meaningful sense. Similarly, if time is emergent, the universe might not have an age in any fundamental sense. The 13.8 billion years might just be a feature of how we observe and measure the emergent spacing, not a property of the underlying reality. Now, let me talk about quantum mechanics and time. In quantum mechanics, the evolution of a system is described by the Schrödinger equation. This equation tells you how the quantum state changes over time. But there's a problem. Time in quantum mechanics is treated differently than space. Time is a parameter. It's not an observable. You can't measure time the way you measure position or momentum. Time just flows inexorably forward in the Schrödinger equation. But in general, relativity, time, and space are on equal footing. They're both parts of space-time. They transform into each other under changes of reference frame. So there's a fundamental tension between quantum mechanics and general relativity in how they treat time, and we don't know how to resolve this tension. We don't have a complete theory of quantum gravity. What this means is that when we try to apply quantum mechanics to the early universe, when quantum effects and gravitational effects are both important, we run into problems. We can't consistently describe what time means. The Schrödinger equation needs an external time parameter, but general relativity says time is part of the dynamical spacing. These two requirements are incompatible. Some approaches to quantum gravity, like the Wheeler-DeWitt equation, try to eliminate time altogether. In these formulations, the universe doesn't evolve in time. It just is. The wave function of the universe is static. Time and the appearance of change are emergent properties that arise when we look at subsystems of the universe. But the universe as a whole is timeless. If this is correct, then the question of the universe's age is meaningless. The universe doesn't have an age because time isn't fundamental. What we experience as the passage of time is just a feature of how we, as observers embedded in the universe, perceive things. It's not a property of the universe itself. Now, you might be thinking, Lenny, this is getting too abstract, too philosophical. We measure the cosmic microwave background. We see distant galaxies. We calculate an age of 13.8 billion years. How can you say that's wrong? And you're right to push back. The observations are real. The measurements are precise. But what I'm saying is that the interpretation of those measurements as the age of the universe is more subtle than it seems than it. When we say the universe is 13.8 billion years old, what we really mean is this. If we model the universe as a homogeneous isotropic expanding spacing, if we assume general relativity is correct on cosmological scales, if we use the reference frame of a co-moving observer, if we extrapolate backward to a time when the universe was very hot and dense, then by our current definition of time and measurement, that was 13.8 billion years ago. That's a lot of assumptions, and each one of them has subtleties and potential problems. Let me tell you what I think is really going on. The universe is vastly more complicated than our current models. We're using approximations. We're ignoring quantum effects. We're ignoring the detailed structure of spacing at small scales. We're assuming that general relativity holds all the way back to the Planck time, even though we know it must break down there. We're treating time as a simple one-dimensional parameter, even though we know it's more complicated than that. The number 13.8 billion years is our best estimate given these approximations. It's a useful number. It helps us understand the history of the universe. It gives us a framework for thinking about cosmology, but it's not the deep, fundamental truth about the age of the universe. Because the age of the universe might not be a well-defined concept at the deepest level. Here's what I've learned after decades of working on these problems. The universe is stranger than we imagine. Time is not what we think it is. The Big Bang is not what we think it is. And our measurements, while precise, are measuring something more subtle and more complicated than a simple age. When I was younger, I thought cosmology was about measuring things. Measuring the age of the universe, measuring the rate of expansion, measuring the density of matter. And that's part of it. But the deeper part of cosmology is about understanding what these measurements mean, about understanding the nature of time and space, about understanding the limits of our theories. And what I've come to believe is that the universe's age is wrong, not because we've measured it incorrectly, but because the question itself is based on assumptions that break down when you really understand general relativity and quantum mechanics. The universe is 13.8 billion years old in approximately the same sense that the Earth is flat. It's a useful approximation for certain purposes, but it's not the fundamental truth. So the next time someone tells you the universe is 13.88 billion years old, ask them who's 13.8 billion years. Ask them what reference frame they're using. Ask them whether they're talking about the observable universe or the entire universe. Ask them how they're treating time near the Big Bang. Ask them whether time is even fundamental or emergent. And you'll find that the simple answer, 13.8 billion years, hides an enormous amount of complexity and uncertainty. That's the truth about the universe's age. It's not a simple number. It's a complicated statement about geometry, about reference frames, about the limits of our theories, about the nature of time itself. And understanding why the number is wrong in this deep sense is far more interesting than knowing the number. After 50 years of thinking about cosmology, I'm more uncertain than ever about what the age of the universe really means. But I'm certain of this. The universe is far stranger and far more wonderful than our simple models suggest. And that's what makes physics exciting. That's what keeps me thinking about these problems even after all these years. The universe always has more to teach us. We just have to be willing to question our assumptions.